sum of those is 0 for mod 6. And if difference between adjacent parts is equal to 4, so I'm saying adjacent parts here. So if you have both so the difference here is 4. So if you have both a 5 and a 9 in your partition, for instance, the sum of those is 2 mod 6. And then you can't have 1, 2, or 4 as those are initial conditions. And again, let's just realize here that's coming from a fictitious 0. If you put in a fictitious 0 into the upper two, you'll see that actually doesn't affect anything, and so it's actually not too surprising that we don't get initial conditions. In terms of this one is a family of 3 of them, that they're all mod 9 kind of thing. So as of right now, we don't have an infinite family of conjectures here. So this is one of the big parts of the talk.
So for the second one up there, which was mod 12,
yeah.
Your infinite family, does 12 stay fixed? Or does
No, okay, yeah, so good question. So when I say infinite family, I think that, this one, it is it goes every 4. So there's
16.
one, yeah, so there's one, so there's one for mod 8. There's probably one for mod 4 that's kind of trivial kind of thing here, mod 8, mod 12, mod 16, so on and so forth.
And just this second condition becomes longer.
Just the second condition becomes longer. And the first one up there, I think it goes for every, so it goes mod 8, mod 6, mod 8, mod 10. Don't want to swear to that. This one right now is just fixed, so just a family of.
Was that the original, Shashank? Matthew?
What's that?
That was the original one?
Okay, yeah. So right. Shashank and I earlier had conjectured some mod 9 ones. This is different here, so let me just elaborate on a couple of important differences from this to stuff that was known before. Number one is that all of these here allow for arbitrary repetition of some parts. So the first and the third one here allow you to pick a part. You can repeat it as many times as you want. The one in the middle, any even number, you can repeat as many times as you want. Everything that Shashank and I did before did not have those conditions on it. Second thing is that the product side is actually radically different than product sides that we've dealt with before. Drew Sills gave a talk at JMM last month, and he and I, Shashank and others, he's been really interested in what product sides are allowable to have partition identities from them, kind of thing. And there was this one condition that he was proposing that is very intriguing, which is that many partition identities, they tend to be, I don't know, this is the word he used, I'll call it kind of balanced. That if you look at the mod condition, everything, so for example, they're symmetric, Rajaramanjan is 1 and 4 mod 5, okay, that's, symmetric mod 5 kind of things. Other ones, they tend to be, there is a, so for example, when one of the Shashank and I mod 9 ones is going to be 2, 3, 5, 8 mod 9. That's not symmetric, but again, the average of the allowable parts is what it's supposed to be, basically. This one, even if we delete this one right in here, the average is not what it's supposed to. It's unbalanced. It's tilted more on this end of the scale than the other ones. So that's kind of unusual. That's kind of surprising. That's part of what makes this, kind of fantastic beast here. So. Okay, and any other, so thanks for asking about it. Other questions right now? Okay, because people have been bugging me about, what's known, what's not known, proof and stuff like that. let me kind of give this up. So the one in the middle we have proofs for. It turns out that this is a dual of a family of Andrews that dates back to about 50 years ago. So we proved it using similar techniques to what he did. We've also generalized it. It turns out that there's connections that there's underlying over partition identity. If you want to know more about that, talk with me afterwards. But we can prove that. The first and the third, we were stuck at for a long time for proofs. And we still don't have proofs, but like I would not be, again, dangerous thing to say on camera, but I would not be surprised if we have proofs from those sooner rather than later. If this talk was a month later, it might, this part of the talk might be looking different. I guess is what I'm trying to get after. So, and there certainly is absolutely no doubt in our minds that they're true.
How much experimental evidence do you want to have a conjecture?
So usually we go, for like the first pass, 30, 40, 50 terms is good. And then if we hit on something that works that long, then we'll usually try to write out some more involved recurrences so we're not just doing brute force, that we're actually, can calculate out many more terms. At that point, it's easy to go out to 1,000, 2,000 terms, stuff like that. That is very, very good evidence, I think. So, okay, other questions right now? Okay, I guess so. The next part of the talk is going to be another place to look for identities. That is kind of this is shifting to some work with Shashank on a different project now. And this is going to be looking for partitions, identities, with Lie theoretic connections. So roughly about 1980, give or take a handful of years, Jim Lepowski and Robert Wilson, both formerly here at Rutgers, came up with, and along with some other collaborators, they came up with some very deep connections between partition identities and various affine Lie algebras. So disclaimer here, I'm certainly not an algebraist by any means. Most of what I do, I'm just using this as a kind of black box. So, what I'm about to say is about the depths of what I actually know, kind of thing here. So for example, if you look at the affine Lie algebra A11, it turns out that this corresponds, and again, this is due to Lepowski and Wilson. They show that these correspond to the Rogers-Ramanujan identity. So plus, 1 or 4 mod 5, 2 or 3 mod 5. I believe they hold, so one of the kind of fun things with that is they hold the record for the longest proof of the Rogers-Ramanujan identity, so 80 pages or so. And so then you can kind of play this game. Okay, A11 is affine Lie algebra, and so you can kind of play a game here. Pick an affine Lie algebra, pick some level of it. Are there partition identities that correspond to it in some ways? So, for example, if you look at A22, you end up with, I'll drop this notation temporarily speaking, 2, 3, 9, and 10, mod 12.
This is much better notation.
But there is one reason. So again, first time doing it, you're about to see one reason that I'm going to use it in the future. That is the reason for me doing this. So this is Caporelli came up with a conjecture and later proof of an identity with product side 2, 3, 9, 10 mod 12. From studying level 3 of A22. Nandi mentioned him earlier. His thesis was exploring level 4 of A22 with a mod 14, with some mod 14 ones there. There's lots of other ones. One of Shashank's thesis chapters dealt with a 5-2, I believe, and show that there's connections with Goldman-Gordon. And so what he, so anyways, like it feels like pick a leaf, pick an affine Lie algebra, what can you do with it? And so at one point, he ended up, I want a fresh piece of white chalk. At one point, he ended up asking me about the affine Lie algebra, A92. So A92, and this is at level 2 standard modules. And so if you take a look at what the Lie theory tells you the product sides are, you get the following product sides. I'm going to revert to this notation again, if you forgive me. You get this for one of them. There's 3 of them in total. 0, 1, 0, minus 1, minus 1, minus 1, 0, 0. So this second one actually has a 1 there. So I can't just say it's, I have to be a little bit particular about distinct, there's a little bit more going on here. So this is why I like the writing in this notation.
Put a clip.
I have a little bit.
And explain to us what it means.
So that was the reason for me torturing you. So he basically asked me, if you take these 3 products, so here are the products. We can use Maple to calculate out as many terms of these as we want. No sweat. What's the product? So this is the product side. What's the sum side?
Just a question: is the 6th position in S2 supposed to be +1?
Yeah,
That's
that was the discussion. Okay, that was the whole reason I'm annoying you with this notation.
That's why we've been looking at all these binary.
Yeah, and I think that I actually, my eyes did not catch that one the first time I tried to code or something like that. So what we did before was, okay, we write down the sum side, this is the product side. We just try lots and lots and lots and lots of sum sides till we find one that has a nice product side. Okay, now we have the product side, what's the sum side? That's the new goal. And then the question is, how do you even start going about, so we could say, okay, so our guess, which is inspired by other stuff, so Shashank and I kind of came up with this guess together. It seems natural that S1, S2, and S3 all satisfy the same difference conditions, but with different initial conditions. Because that seems to be what typically happens here. So, that is. Okay, so with Maple, we can easily write down kind of like what S1 is equal to 1 plus Q squared plus Q cubed plus 2Q to the 4th plus 2Q to the 5th plus 3Q to the 6th plus 3Q to the 7th. And then S2 is equal to 1 plus Q squared plus Q cubed plus 2Q to the 4th plus Q to the 5th plus 2Q to the 6th plus 2Q to the 7th. S3 is equal to 1, and then the first one is at Q to the 4th. I'm getting bored of this, so we're to stop there. And so, okay, we have this. What do we do with this? And so our idea that we came up with was just to kind of try to do one sort of, almost like a setup on it kind of thing. So like start off with, so if you just start off by allowing any part, all partitions kind of thing, and then just, okay, you're going to be over counting, I just, do the all partitions. That's, that generating function is going to be bigger than all of these, and then just chop out some kind of conditions here. until you get down to what you're aiming for. And so I use a computer. So there's kind of nice collaboration here between me and the computer. That's was familiar for the seminar. When that is not the right piece of paper. Which piece of paper is it? Must have been back over here. How many pieces of paper? This was a piece of paper. So,
quasi-coherent sheet.
yes. I don't think I've ever made more pieces of paper notes for a talk than this one. I write very, very large, so lots of pieces of paper. So let's kind of look at this S1. So, okay, there's one partition of 0 in general, there's one partition of 1. There's two partitions of 2, but we only want one of them. And so the question is, do we want to band 2 or do we want to band 1 plus 1? It feels more natural to band 1 plus 1. Let's have this here. Let's have the bad ones be written over there. So it feels natural to band 1 plus 1. Okay, now we have 3, 2, or 1 plus 1 plus 1. Well, this one's already banned because we already have, forbid, 1 plus 1. So it feels like that one should get banned as well. Oh, sorry, 2 plus 1 there. And then it feels more, it feels more natural to ban this, but like the closer together they are, that feels like the worse it should be, kind of thing. And so maybe we're going to ban 2 plus 1. And then we just keep playing this game. I mean, obviously there's going to be some intuition going on here, q to the 4th, so 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1, which one do you want to band there, kind of thing. And also we're kind of doing this, we can do this simultaneously for all 3 of these, because we want some conditions to be the same for all of them, some condition, along with some initial conditions. And after some experimentation, that I'll kind of gloss over all the steps. You start getting a list that looks like, 1 plus 1, 2 plus 1, like a 3 plus 2 appeared here, a 3 plus 3 appeared in my list, a 5 plus 5 appeared, a 4 plus 3 appeared, a 4 plus 4 plus 1 appeared, a 4 plus 4 plus 2, 6 plus 6 plus 3, 6 plus 6 plus 4, 4 plus 2 plus 2, 5 plus 2 plus 2, 6 plus 4 plus 4, 7 plus 4 plus 4. And so after a little bit of studying, like this took a while again, there's some intuition going on here. So you start to realize that there's that all of the stuff I was forbidding here broke down into some nice categories. Like, it seems like we could never have repeated parts. We could never have, sorry, we can't have consecutive parts. We can't have repeated parts. One more that I was forgetting here. There is a 2 plus 2 plus 2, a 4 plus 4 plus 4. So you could repeat even parts, but at most twice. 3 is a no-go. And then if you did repeat your even part twice, then you couldn't have this 1 or this 2. It forced the next one in either direction to be at least 4 away. And that seemed to go for all of these. And so I am basically right at 547, so I won't, but I won't write out. But again, we have, there's conjectures that basically just formally write down what, this picture here of those 3, one for each one of those, slightly different initial conditions, and each one figure out. But again, it's just kind of like knowing where to look. The affine, I'm treating, I'll be honest, I'm treating this affine Lie theory just black box kind of thing. I know, okay, this might be a place to look, and so I look there, and hey, look, fantastic identity. So I guess that is, I'll be wrapping up right now. If you want to talk about, so there won't be time for questions, I'm ending right on time. If you want to talk to me afterwards, I'd be delighted to discuss any of this. I will take the camera to apologize. There's, I said I'd be doing 3 things. Didn't get time to present what I did with Jongwon and Terence last summer, although I presented that at JMM, so that will kind of make up for that. So, thank you all for your attention.
Thanks for fantastic. Maybe we get to answer questions in private.